Okay, so good morning, students. Am I audible?
Yes, sir.
Okay, so unfortunately, there was a lot of administrative work regarding the NAC accreditation in the college. So that is why I was unable to take the classes because I was busy in those administrative work. So that is also the reason why the exam got postponed. Okay, so it is going to be start from 31st. Okay, so the syllabus will be remaining as it was discussed or it was shared in the Google Classroom. So all of you must have seen the syllabus of my subject. Okay. So we have lost a few classes also. So okay, so I will try to cover those before the semester exam comes. Okay, because we still have a few more time left. So okay, so in the last class, as I have as I can remember and I have seen from the recording that we have started the magnetostatic. Okay, so we have started this particular magnetostatic field. Okay, we have discussed this portion. Okay, so we have discussed this portion. Okay, so we have some discussed some numericals also, if you can remember. So now I will be continuing the next part. Okay, the next I will continue this particular topic. Okay, where we have left. So now we will discuss about the Ampere circuital law. So now the thing is Ampere circuital law. This portion was there in the basic electrical also. Okay, that means it is related to the magnetostatic itself. That when there is a current flowing in a conductor. So when there is a current in a conductor, the conductor produces some magnetic field. Okay, that we have already seen in the previous lectures. That the current, when it is passing through a direction, suppose the current is passing through a conductor and you point your thumb towards the flow of current. Okay, then if you curl your fingers across your palm, that means in that direction, okay, the magnetic field will be produced. And if you see from the top view, suppose you are seeing the conductor from the top, then the magnetic field lines will be in the anticlockwise direction. Now more the amount of current, more is the radius of the magnetic field, the circle, concentric circles. Okay. Now when that particular field is created, okay, so within that field, similar to electrostatic, where we know that when there is a charge, it is creating some electric field. So at any point within the field, there is some electric field intensity, okay, which is represented by capital E. Similarly, in magnetic field also, when the magnetic field is created by any current, okay, that is called the electromagnetic field. So there also, within the field, at any point, you will find some magnetic field intensity, okay, that is represented by the letter capital H. Now, Ampere's circular law says that the line integral of the tangential component of H around a closed path is same as the net current enclosed by that path, which means, okay, so which means that if there is a conductor like this, okay, a conductor like this, and the magnetic field will be created in this fashion, okay, okay, in this way. The current direction is like this. So any point in this particular magnetic field, there will be some magnetic field intensity H. Now there is H over here also, over here, okay. So now the statement is that the line integral of the tangential component of H around a closed path. That means the tangential component means if you take the tangential component like this, okay. Here also we have some H, we take the tangential component. Here also we have some H, we have to take the tangential component. That means we take the tangential component of H, okay, along the entire closed path, because it is having some length, okay, it is having some length. So if you take the integral of the tangential component, okay, of H around a closed path is same as the net current enclosed. That means it is equal to the current I, because this H is proportional to I. More is the current, more is the magnetic field intensity. Okay, so in other words, the line integral of H, closed line integral of H equals to I, enclosed current. Okay, the Ampere's law is similar to Gauss law and it is easily applied to determine H when the current distribution is symmetrical. So in Gauss law we have seen that what happens in Gauss law, there is a particular charge, okay, Q within the particular you can say object, and the fluxes are coming out. That total flux is equals to total charge. Here the thing is, it is not the total flux but actually the fluxes, because the magnetic field lines which is there, you can say this is the magnetic field lines, okay, these are the magnetic field lines. So these are actually fluxes created by fluxes, B, flux density, or rather by flux, okay, and flux per area gives you flux density. It is known to you. Now this magnetic field lines which is created by the fluxes, and now in the particular magnetic field any particular point, you will find the magnetic field intensity. Okay, so you will find the magnetic field intensity. Now the relationship which was there in the case of, you can say, Gauss law. What was Gauss law? Q equals to mu. Okay, here it is not Q equals to mu, because here we have H equals to I, because the magnetic field intensity is equals to the current. Okay, because current is creating the magnetic field, which is the fluxes, and any point in the magnetic field you will have some intensity. So here the relationship is a little bit different but similar to Gauss law. But we don't write directly H, because it cannot be represented in that, because it cannot be derived, because the H is proportional to I, but it is not exactly equals to I. Okay. So how it is exactly equals to I current? It depends upon the total sum of the H along the total surface. So that is why we take the closed line integral. Total sum of H along the surface. So we have to take the tangential component, because H is a vector. H is a vector, so it has to be a tangential component, then we can take the line integral. Okay. It should be noted that equation number 1 always holds whether the current distribution is symmetrical or not. But we can only use the equation to determine H when symmetrical current distribution exists. Because current has to be symmetrical. Because obviously in a conductor, current is always symmetrical observed. But in any case, if it is not symmetrical, then this relationship cannot be defined. Okay. Ampere circuital law is a special case of Biot-Savart law. Okay, Biot-Savart law, once again I am going to the previous lecture where we have discussed the Biot-Savart law. Okay, this was the Biot-Savart law, where we have expressed the equation of force. Okay, not force actually, H, but with relationship with a force. That means what is H? Okay, so that means the expression for the magnetic field intensity, H. Magnetic field intensity at a point, how it is determined? Okay, so it is determined in this way, that it is proportional to the current element, IDL. If you can remember, we call this current element IDL. Okay, we call this current element IDL. It is proportional to IDL and the angle between that particular current element and the length, distance. Okay, that is alpha, sine of that alpha. Okay, and inversely proportional to the square of the distance, because it is creating some magnetic field like this. So what is the intensity at this particular point? Magnetic field intensity is equals to this equation. Now you can see it is proportional to IDL. Okay, so that is one expression. But if you take the value of, suppose this is dH, so H will be total integration. Okay, total integration. That is H. So this is the value of H at that particular point. At that particular point, you have a value of H. Now there are multiple points. Okay, infinite points. If the magnetic field intensity is like this, there are infinite points. So if you take the tangential component everywhere along the closed surface, okay, that is the total value of H along the closed surface, that is equals to the I current. This I current. Okay, this is the Ampere circuital law. Okay. Now, taking this equation of Ampere circuital law, we apply the Stokes theorem. What is Stokes theorem? Where we convert the surface integral to a line integral. Okay. So Stokes theorem we can do. This is the line integral, closed line integral. We are converting to a surface integral. Okay. Where it is equals to the closed line integral of a vector, which is equals to the surface integral of curl of the vector. Okay. This is the transformation using the Stokes theorem, which we already know. Okay. But this is the expression for current enclosed. Now, in any conductor, this term is being incorporated. What is J? J is also being represented earlier. The J is the current density. It is the current density. Let me write over here. So J is nothing but the current density. Okay, it is the current density. What is current density? It is ampere per meter square. Which is ampere per meter square. Okay. Okay, so it is ampere per meter square current density. Now the thing is, this is J. So now, if you have a conductor like this, if you have a conductor and the current flowing through the conductor is I. Okay. Now the conductor is having, it is obviously not a thin line like this, it is obviously having, it is a cylindrical shaped conductor. Okay. So it is having some surface area. So the total amount of current which is passing through that particular conductor and coming out of the surface S, area S, that is equals to J. That is equals to J. Okay. So obviously then J will be equals to I by S. So I will be equals to J into S, J into S, J into S cross S, or whatever. Now, VS you can use the cross sign also. Now, what current density? J is actually a vector. Yes, J is a vector. Okay, and here is also a vector. So J cross S we can write because current is not a vector. IDL is a vector. Okay. So that is why we have written in this way that I is equals to integration of surface integration of J. Okay. Okay. So it is the surface integral of J. So current is equals to surface integral of J. So comparing the surface integrals in equation number 2 and 3 clearly reveals that the curl of H equals to J. Why? Because if you compare these two equations, this we know this is the Ampere circuital law. This is the Ampere circuital law. And using the Stokes theorem, we have converted this equation to this equation. Okay. Now this is known to us. This we know. So what we are doing, we are comparing this portion with this portion. We are comparing them. Once we compare, what we have got? We have got that surface integral of curl of H ds is equals to surface integral of J. So what we have these two terms common. Okay, curl of H equals to J. So this is the third Maxwell's equation. This is the third Maxwell's equation. Okay. It is essentially the Ampere circular law in differential form. So this is the differential form because when you will be, I will show you the list of the particular Ampere circuit, these particular, just say Maxwell's equations. Over there, you will see that every Maxwell's equations has a integral form as well as a differential form. Okay. So the integral form is this one. This is the third Maxwell's equation. This is the integral form, which is the Ampere circular law. And if you find the differential form means you will just have to eliminate this integration. You have to eliminate this integration. So once you eliminate this integration, so that means we have to eliminate this integration in such a way by not taking the derivative. Because we have already seen this kind of transformation in the previous two Maxwell's equations also, where we have seen that we don't find the derivative of this equation to remove the integration. What we do, we have an expression where on the left hand side we have an integration, on the right hand side we don't have an integration. So what we do, on the right hand side where we don't have integration, we replace that particular term with a term which is having an integration. Okay, so how to do that? Because you can see it is current. So current, that means it is equals to surface integral of J, current density. So we have replaced I as surface integral of j ds. But on the LHS we have line integral, and in the RHS we have a surface integral. So we have to transform the line integral to surface integral also for the LHS. What we can do, we will apply the Stokes theorem. Applying Stokes theorem, we have transformed the line integral to a surface integral. So what we can see over here, this is the thing where we are concentrating on Stokes theorem, not I. I is just the expression that I equals to this. But what we are doing, we are transforming this one to line integral to surface integral. Now we have this product with us. Now we transform this or replace I equals to this. So we have two surface integral, so they can be cancelled. So this is the way we find the differential equation, the differential form of the Maxwell's equation. Okay. So this is the differential form, and equation number 1 is the integral form. This equation, this one. Okay. So from equation number 6, we should observe that curl of H equals to J. So curl of the magnetic field intensity is equals to the current density. Okay. Now obviously it cannot be equals to 0. So it has to be not equals to 0. Because if you don't have a current, you will not have current density, and if you don't have current, you will not have the magnetic field intensity also, H value. If there is no current, there is no magnetic field, isn't it? That means this has to be a non-zero value. So it is not a conservative. So magnetostatic field is not conservative. Because you can remember, there was a relationship that a curl of any vector, if it is 0, that vector is considered to be a conservative vector. But here, magnetic field intensity H, if you are finding the curl of H, it is 0. That means it is conservative. So it is not possible. It cannot be 0, because if current is not there, H is not there. Okay. So current has to be there. Okay. So curl of H is not 0, because if curl of H is 0, that means H itself is 0. Okay. So it is not possible. So that is why curl of H is not 0. It is equals to J, the current density, and it is a not conservative vector. Okay. Now, coming to the equation of B and H. Similar to the electric field intensity, where we have seen that the electric flux density D, which was electric flux by area, okay, flux density, and D was equals to mu E, where E was the electric field intensity. Okay, here B is the magnetic flux density. That means B equals to magnetic flux per area. Okay, similar to electric flux density, because both are similar, because both this is a magnetic flux and this is a electric flux. Okay, two fluxes are there. This is Weber per area, Weber per area. Okay, but this is not Weber actually. This is Weber, but this is actually Coulomb. Why Coulomb? Because electric flux intensity is called to be Coulomb. Why? Because electric flux is equals to electric charge as per the Gauss law. That is why it is Coulomb per meter square. Coulomb per meter square. But for magnetic flux it is Weber per meter square. WB, Weber per meter square, or Tesla, capital T. Okay, after the famous electrical engineer scientist Nikola Tesla. So this is the magnetic flux. So magnetic flux intensity, magnetic flux density is also having a relationship with the electric flux, magnetic field intensity. Similar to D equals to mu E, here we have B equals to, D equals to epsilon E, we have B equals to mu H, where H is the magnetic field intensity. And mu naught means the permeability of the free space. Epsilon is permittivity of a material, of a conductor, and mu is the permeability of a particular, you can say, dielectric medium, free space, or a magnetic material, or ferromagnetic material, because permeability is very much important, significant for the determination of the how strong a magnetic field can be created if you take a particular ferromagnetic material as a core. Because if you take a ferromagnetic material as a core, say magnetic material A, if it is having a mu value of 1.5, and if you take a ferromagnetic material B which is having a mu value of 3 double, so obviously the ferromagnetic material having permeability 3 will produce more magnetic field because it is having more amount of, you can say, permeability. That is why it can be a better electromagnet. Okay. Now for free space, it is having a constant value which is called the permeability of free space mu naught, which is equal to 4 pi into 10 to the power minus 7 Henry per meter. And this is represented by psi also. Often it is represented. You can represent it by phi, whatever. Okay, both are same, pi or psi. So B is equals to flux by area. So flux equals to flux density into area. So it is surface integral of the flux density. Okay. Now, mu is the flux which is in Weber's. Okay. Now the magnetic flux lines in the, see this one we have already discussed previously. So it is written in a theoretical portion. Okay, where you can I will share it to you with you. You can go through this. So suppose you take a bar magnet like this, north pole and south pole, very tiny bar magnet. Now if you know that any bar magnet has both north pole and south pole, even if you take a solenoid, if you create an electromagnet taking a ferromagnetic material, and if you wind the conductor across it, and if you connect to a electrical supply, this will create a electromagnet. It will also have a north pole and south pole. Okay, so magnetic monopole cannot exist. Now once it is having north pole and south pole, so it will, the fluxes will be like this. Okay, coming out from north pole and entering the south pole. So that means this is not a bar magnet actually. It is representing as a bar magnet, but what is creating this magnetic field? This particular current conductor. Okay, so if you take a conductor like this, then as we have already discussed, that if you take the top view, because from the top view you can see that the magnetic field lines are in a anti-clockwise direction, as if you are putting a bar magnet and the magnetic field lines are originating from the north pole and sinking at the south pole. So magnetic flux lines is the path to which B is tangential at every point in the magnetic field. It is a line along which the needle of a magnetic compass will orient itself if the placed in the magnetic field. Yes, if you take how this was actually discovered, because you cannot see the magnetic field lines, isn't it? Obviously, if you take a current, if you pass a current through it, you will see that if you're connecting a bulb, you will see current, the bulb is glowing. That means current exists, electrical energy exists. That we know. But it is creating a magnetic field that was not discovered instantly. Because after the discovery of the electricity, okay, it was not discovered that it can create a magnetic field also. Okay. Then it was discovered that it can create a magnetic field. Then the real application of the generator was implemented. So how it was discovered? One scientist was experimenting some particular experiment, doing a work on an experiment where there was a line conductor, a particular conductor, and current was flowing. Now there was some compass, okay, below that particular conductor. So the compass needle was deflecting. So more the current was flowing, more was the deflection. So that struck him. So why it is deflecting? Because a compass shows north pole, points towards the north pole of the surface earth, and south pole. So why? Because it acts on the magnetic field of the earth. Okay, this is one point. And if you take any bar magnet close to a compass, then that compass needle will also deflect. That is why in the compass where it was used in the ships, okay, and it was used in many vehicles also, because if you drive a vehicle, now we have all GPS and all these things, okay, but in the dense forest also, when mobile tower is not there or internet tower is not there, So what was actually there, or what was actually the way people used to travel in the forest? By using a compass, because they used to know that I have to go, say, 30 degrees south, northeast, or suppose southwest. Okay, that means he has to take the compass and travel through the forest in that particular direction. Okay. Okay. But if you take any any particular steel or a iron material object towards it, then it will attract and the needle will point towards that object. That is not desirable, because you are traveling in a forest, and if the needle is not showing the actual north pole, rather it is deflecting. North pole is deflected towards the iron material which is kept beside the compass. That means it will show the wrong direction. If you continue to travel in that direction, you will be lost. Okay, so that is why a compass always deflects according to the you can say the geographical particular magnetic field, or any particular iron object or ferromagnetic material. It will deflect towards it because it will try to attract. Okay, because if it is within the magnetic field, it will try to attract. So now, if you take a conductor and if you put a particular a particular compass close to it, the north pole will deflect. Okay, it will deflect, and if you try to orient in such a way that it will try to, you can say, deflect along the magnetic field of that particular conductor current. So you take a north pole and south pole. Okay, if you take a north pole and south pole, and if you put it over here, you can see it will orient in this way. Suppose you take a random north pole and south pole like this. Okay, or bar magnet like this. Okay, north pole and south pole. Once you bring close to it, it will deflect, it will bend, and it will point in this direction, as if north pole is pointing to in this direction, south pole in this direction. If you put a magnet over here, you will see that the needle will deflect, orient itself in this direction. ऐसा शेप में आ जाएगा, ठीक है, नॉर्थ पोल साउथ पोल इसमें भी ऐसे शेप में आ जाएगा. So by putting this, they used to draw the lines using scale or pen. They used to put north pole, south pole like this. You have to take 2 points, and again they have to put the compass over here. You will see that north pole and south pole has taken this kind of a shape. This shape. This shape, north pole, south pole. So they used to take these points and they used to join them. After joining them, they have seen that it is kind of a circle. And obviously north pole will point towards in this direction, that magnetic fluxes are coming out from north and entering south. That is why they have told that it is in the anti-clockwise direction from the top view. And from the side view, it is like a right hand curve. That was the conclusion. Okay. So the direction of B is taken as that indicated by the knot by the needle of the magnetic compass. Notice that each flux line is closed and has no beginning or end. So it is a closed flux lines. Why? Because we are having north pole and south pole. Whereas if you take the Gauss law, for example, Q, the fluxes are coming out. It is originating only. It is not converging. The fluxes are coming out. But in magnetic field, fluxes always converge because they start from north pole and ends at south pole. Even for a conductor also, current carrying conductor also, because there is a magnetic field. Though the figure 1 is for a straight conductor, current carrying conductor, it is generally true that magnetic flux lines are closed and do not cross each other regardless of the current distribution. If the current is more, the radius will increase, but they will not ever cross. This uniform gap will always there. It will always be a concentric circle, a perfect circle like this. It will go on. More is the current, bigger is the area, and more is the concentric circles. Okay. Okay, so we will continue this next portion in the next class. If you have any question, you can ask. Okay. Is it understood?
Yes, sir.
Okay. Okay, so I'm ending today's lecture up to here. So you can continue with the notes which I have already provided. because the internal exam is there. And after this magnetic static field, we will continue with the next chapter. Okay, later. I will try to wrap up within the month of February itself. Okay, before the exam. If required, I may take some extra classes also. Okay. Okay, so thank you then, students.
Thank you, sir.